Cool. Hey, everybody. So today, topic 27, K-nearest neighbors. And K-nearest neighbors is just another classification algorithm that we're going to talk about today. But today, we're going to be talking about K-nearest neighbors in the context of classification. As you can see here, I'm going to go through this documentation a little bit. But there's also a K-nearest neighbors regression regressor. And I just wanted to let you all know that that exists because if you ever end up doing another regression project, for example, predicting another continuous variable perhaps for your capstone, know that a lot of the models that we're going to be talking about this week and next week all have regression counterparts. You just have to look them up. So K-nearest neighbors regressor does exist, pretty much like works the same way. Not going to go through this today, but in case you ever do another regression project, remember that this exists. All right, so K-nearest neighbors. We're going to talk about some distance metrics because we're figuring out nearest, and nearest can be, dependent on what metric you choose. And then we'll talk about implementing K-nearest neighbors. Before that, wanted to talk about some statistical definitions. If you ever hear the words parametric, non-parametric being used in the context of models, this is what that is. So parametric models are models that we've talked about so far. So linear regression is parametric. Logistic regression is also parametric. The models that we're going to talk about today and tomorrow. So tomorrow we're going to hit decision trees. No, that's not correct. Decision trees is going to be next week, but tomorrow we're going to hit, I want to say naive Bayes, which is also non-parametric, by the way. So non-parametric models, K-nearest neighbors, K-means, decision trees. These are non-parametric models because parametric models basically make assumptions on the underlying data distribution. So when we were doing our linear regression, and yesterday when we talked about logistic regression, there are some assumptions that have to be fulfilled for our model to be, reliable, consistent, so on and so forth. So non-parametric models, of which K-nearest neighbors is one, allow us to apply models to data that are not normally distributed or not distributed in any specific or specified way. So therefore, if assumptions of your data not met, you can just use non-parametric algorithms and you don't have to worry about, relationship between your variables. Neither do you have to worry about things like multicollinearity. You don't have to worry about, having to transform anything. A lot of times with non-parametric models for your data, no assumptions that you have to worry about. So if some assumptions of your data are not met, you can use non-parametric algorithms. An important note, we only say that our models are parametric, not parametric, not our data. So quick definition, parametric models are ones that just have underlying assumptions for the data, and non-parametric ones do not. Cool. Next, we're going to talk about distance metrics because this is really going to help lead into K-nearest neighbors. So there are many different ways mathematically that we can compute distance between 2 points or two data points. So we're going to go through some of the more common ones. First one is Manhattan distance. Manhattan distance is just the sum of the absolute values of the Cartesian coordinates. What that means, we'll get into a little bit. You can sort of think of Manhattan distance as moving through grids. So in the image below, only the green line is infeasible to calculate Manhattan distance, this green line that goes diagonally across. So anything that just calculates like, perpendicular roads, that would be Manhattan distance. So the distance of the red, blue, and yellow lines are actually all equal in this scenario. So equation for calculating Manhattan distance is just take the difference between the coordinates. So as a quick example over here, if we have point A being 2 and 4, let's just imagine there's just two features here. We have 2 and 4, point B, we have -1 and 5. You can calculate Manhattan distance by just adding the absolute difference between each corresponding coordinate. So your Manhattan distance will be 4 because the difference between this is 3, difference between this is 1, adds up to 4. So it's really just a difference in the feature values. So that's probably the most basic one. Scaling up, we have Euclidean distance, which is pretty much the same thing as like our Pythagoras theorem. So Pythagoras theorem is Euclidean distance. It is the most common used distance metric. And to calculate Euclidean distance, again, Pythagoras theorem. So you have your 2x points squared plus 2y points squared. And then you're just taking the square root of that. So another function to calculate Euclidean distance. Here we're doing it manually. I'll tell you that all of these functions or blocks of code, there are actually built-in methods to do this, not manually, but just to show you all, we're adding the square of the differences and then taking the square root of the total. So Euclidean distance ends up at 3.16 compared to before we had 4. Cool. Finally, there's Minkowski distance, and Minkowski distance is actually generalized. So it's a generalized format of our Euclidean distance. So Minkowski distance, you are varying R. So Manhattan distance and Euclidean distance are basically cases of Minkowski distance where R is equal to, I want to say 0 and 2, or sorry, 1 and 2 respectively. So that's just another name for, it's just another distance metric, and Minkowski distance, you'll tell it, for example, if Minkowski distance with a value of 3 is pretty much the same formula as Euclidean distance. Instead of taking a square root, you're taking a cube root. If you have Minkowski distance of 4, you're going to take a 4th root instead of a square. So if you ever see that word Minkowski, it's just the generalized form of our Euclidean distance. Cool. Questions about distance metrics? There are actually a few others that we're going to touch on throughout the rest of this program. Any questions about measuring distance? Cool. So measuring the distance between data points is important for K-nearest neighbors because the algorithm is built upon distances between points. So here's a pretty neat illustration to demonstrate what K-nearest neighbors is doing. So KNN is simple, non-parametric, and lazy algorithm that can be used for both regression and classification. Earlier, I showed you all that we're going to go through this K-nearest classifier documentation, but there's also a regression counterpart, works the exact same way. Non-parametric because, again, doesn't make any assumptions of the underlying data distribution, and it is lazy because it doesn't learn a function from the training data, but it kind of memorizes the training data instead, and I'll talk more about that in a little bit. The algorithm basically ascribes class membership based on the closest K neighbors to the test observation concerned. And KNN is a similarity-based algorithm. The class membership only depends on feature similarity to training observations. So as an example, let's just say that these red and blue points here are all from our training set. So this is our training set. Now in our test set, we have this new green circle here. So K-nearest neighbors is basically how it works is we're going to see, okay, I'm going to look at what my neighboring points look like, and I'll basically be classified as the class that is most common, or yeah, that is most common. So for example, in K-nearest neighbors, you can sort of say how many neighbors you want to look at. That's one of the hyperparameters that we're going to tune in a little bit. But let's just say I want to consider just my closest neighbor. So my closest neighbor here, as you can see, k equals to 1 is in this small ring here. So k equal to 1, my closest neighbor is this blue square, which is class 1. So with k equals to 1, the classification of this green circle is going to be class 1. It's going to basically say, oh, it's a blue square. If we increase the number of neighbors to k equal to 3, so k equal to 3, we have this larger circle. Now within this radius, we have 1 blue square and 2 red triangles. And because the number of red triangles outweighs the number of squares, we're going to say, okay, that green circle is class 2. So different values of k can actually give you different results depending on, where your points are distributed. And that's really how this algorithm works. In a regression case, kind of similar, you sort of see which data points are closest to your test data point, and you're sort of like taking an average of their target values as well. So similarity depends on the distance of observations from each other, which can be calculated using any of the distance metrics that we talked about earlier. And the most commonly used distance metric is Euclidean distance. However, which distance metric you use, as well as the value of K, can affect the performance of your model. So the decision boundary, we'll talk about decision boundaries in a little bit, can change accordingly to different values of K. So simply put, this is really how K-nearest neighbors works. The one thing I want to point out here, it memorizes the training data set. Now this is a lazy method, but is actually quite memory inefficient. So how in the backend K-nearest neighbors works is actually saving distances between every single point and every single test data point in your data set. So it's actually storing a lot of distance values and then figuring out which are the neighbors and then figure out what class your neighbors are and then therefore classifying your middle point. So yeah, some cons, I guess. Questions about this before we get into our implementation? Sweet. All right. So we're going to use the same data set that we used yesterday, that iris data set. So EDA is going to be in yesterday's notebook. So here we're loading our iris data set. We have our X and our Y. This is before we do our train test split. So cool. We have 150 data points. If you remember from yesterday, it's like 50 per 3 classes. And then we're going to import our K-nearest class, K-neighbors classifier. So the steps are exactly the same steps that we used for our logistic regression yesterday. So first we instantiate it. And when we instantiate it, we're going to start with just one neighbor first, and we'll see how it works. And then you fit your model and you can make your predictions. So a couple ways to make predictions. First, you can do your KNN.predict. KNN.predict, and you can predict on X and you get all of your predictions over here. Something that I didn't talk about yesterday, but I did mention slightly how you would do this in scikit-learn for linear regression. But basically, if you want to make predictions on unseen data, like data that isn't even in your test set, this is how you would go about it. So I know that this data set, based on what my X looks like, my X has 4 columns of data. And each of these lists represents the data for a single data point. All I have to do is feed it in data of the same shape, and it can make a prediction. So I'm just using KNN.predict. I don't even know what these are. I don't remember what these are. Let's find out. Okay, I think it's sepal petal width and length. Yeah, that's what it is. Make a prediction. It'll say that it's class 2. I can also do this on multiple unseen data arrays, and the first one is going to be 2, second one is going to be 1. So that's how you can make unseen prediction. This is going to come back when we get to our project. Cool. So what we can do here, again, we went through this again. We're instantiating our model, fitting the model, and predicting. So as you can see, for all scikit-learn models, even the ones that we're going to talk about tomorrow, even the ones that we're going to talk about next week, procedurally work exactly the same. So this is kind of alluding to, and I'll talk about that actually right after this whole notebook. This is going to allude to the task that I'm going to have you all work on, which is basically to write a function that does this for you.
Real quick. So
Yeah.
the 3542, you went a little fast for me there.
Sorry.
No, it's no problem. Is it that those are 4 different data points, or is that all from one data point?
This is all from one data point, and because my X data, sorry, I know I speak pretty fast, a lot of coffee this morning, but okay, in this data set, there are 4 features. And since there are 4 features for each data point, my input data has to be of length 4 as well. So yes, this is just for one data point, and this is
right.
for
So
2
those are
data
4
points.
features from that data point. And do they have to, and they're obviously in the same order, I presume, as the.
Yes, the order has to match.
Thank you.
Awesome, good question. Sorry, I'm going to try and slow down while I speak. If I'm ever speaking too fast, someone please let me know. Okay, cool. Now let's just put it all together in one coherent project-like procedure. So we have our data set, we have our X and Y separated, and this is just assuming that we don't have to do any data cleaning. This data set only has 150 data points, so we don't have to do any data cleaning here. But we've done our EDA. We're just going to do our train test split. I'll talk about scalar in a little bit, but here we're scaling our data, and then we're fitting our model and making predictions. So this is all being done in these steps. And then from here, we can take a look at our results. If you remember from yesterday, the two most important things to see that I want to see in your projects are the confusion matrix and your classification report. And preferably for both your train and your test set, so you can check for overfitting. So let's take a quick look. This is our confusion matrix for our training set. This is for our test set and our classification reports for our train and test. Perfect classification that we have over here. So cool. For every model that you run, it is good to see all of this output. So again, whenever you're writing your function, which I'll talk more about in a little bit, I would like to see all of these outputs, and the way that you want to display these outputs or the way that you want to format your function is completely up to you. Okay, now back to scaling. So for KNearest Neighbors, not for every model that we're going to talk about, but for KNearest Neighbors, it is quite important that you do scale your data. Reason for that is KNearest Neighbors is a distance-based model. So imagine that we were doing classification for your housing prices again. And let's just say you divide your houses into, let's say, 5 different tiers of how expensive they are. Your features, you have features like you have dummy variables such as like waterfront. I know a lot of you use that. That was a dummy variable. You have dummy variables for like your basement, for example, but at the same time, you have numbers like square footage. You have numbers like, square foot living, 15 square foot lot, and all of those. And those are measured in like the thousands, like the hundreds and the thousands. And so when you're computing distance, especially if you're using one of the distance metrics that I talked about before here, the different scales of your features is going to lead to some bias in how your model measures distance between data points. So for example, anything that has, very different square footages are going to be seen as having, a much greater difference because square foot is measured in the thousands versus your dummy variables only being measured 0 to 1. So the dummy variable distance is going to be much smaller. Those other features much bigger. So it is pretty important to scale your data such that they're all being considered equally. Now, when things get more advanced and you want to tell your model, hey, I want to prioritize these features and deprioritize another set of features, you can actually play around with different kinds of scaling. Like, for example, I did a project once where I was actually using some sort of KNearest Neighbors like algorithm to recommend board games. I actually worked on a project like this a couple years ago, and there's a lot of features about board games, right? Number of players, different genres of board games, I don't know, different creators, countries that they came from, number of languages, a lot of different features. And some of them I wanted to emphasize, right? Like, for example, if I'm making a recommendation, I don't want to consider like the color of the box as importantly as, let's say, the genre of the board game. And so with that, I was actually playing with, okay, I'm going to scale up the features that I think are more important, scale down features that I don't. So you can definitely play around with that. Not for this project, I would say, but in the future, anything that uses any sort of like distance-based approach, you can really get really creative with how you want to play around with computing distance. So just tidbit that's good to know. But anyways, that is why it's important for any distance-based model, such as KNearest Neighbors. We're going to touch on a couple others. I want to say not this phase, but next phase. That you scale your data such that all your features are being considered equally. But that's why we have here. We're fitting our scalar, transforming both our train and test. Cool. And any questions at this point? Because procedurally, we sort of did this yesterday.
So for all of the models that we're using for this project, we're going to have to scale the data?
Not every model needs scaling.
Be, in the function or not.
Good question. So I'm going to talk about it on Friday. There's a tactic where you can actually choose to have a scalar or not a scalar. So I would say write your function, or if you're already starting to think about this function, write it without a scalar.
Okay.
Write it without a scalar to begin with, because I'm going to talk about a method where you can create a model that incorporates a scalar. But I'll talk about that on Friday, not today. yeah, so if anyone, especially those of you who indicated that you want to work on this project by yourselves, you can pretty much get started if you want, but no pressure at all by any means. But yeah, I'm gonna go through on Friday as I talk about the project methods that you can use to automate your modeling process. But yeah, great question. Anything else? Okay, so KNearest Neighbors basically looks at K number of nearest closest to any test data point. So as you can see here, the number K that you choose to use for your model can really affect the performance. So let's play around with different values of K in this data set. So what I'm going to do here is a process known as hyperparameter tuning, which as we get more and more complicated with our models, which we will next week, we're going to see more and more different hyperparameters to tune. But basically for KNearest Neighbors, the main one to tune is K. You can actually see a list of hyperparameters from here. So N neighbors, as you can see, the default is actually 5 neighbors. You also have weights, which is pretty interesting to play around with as well. If you want to tune different weights, you can instantiate one with uniform weights, one with distance weights. Here you can also use a different algorithm to quickly compute nearest neighbors. These are optimization algorithms, so not super important for us right now. But yeah, a bunch of other things. I think there's another one that tells you what kind of this. Oh, here we go. What kind of distance metric you want to use, you can also tune. By default is Minkowski distance with p equals to 2, which is basically Euclidean distance. So we're going to stick with this now, but I'll sort of show you how you can tune that. First, the most important parameter that you want to tune for KNearest Neighbors is what value of K. So what I'm doing here is I'm going to test values of K from 1 all the way to 40. I'm going to append train and test scores just to see how the model performs with different K values. So here I'm doing that. These are all our scores just to make it easier to read instead of looking at this printout. Let's plot them on a graph. So interesting. As you saw earlier, when we had our very first model with K equals to 1, we had perfect classification, which, as you know, you should be skeptical of if you have perfect classification. But it really depends on context, really depends on your data. But as you can see here, your train and test data, your train and test metrics, and this is accuracy score, starts to go down as we increase the value of K. That's because at like K equals to 40, we're considering the 40 nearest neighbors to a data point, and it really depends on how they are distributed. Maybe, yeah, it really depends on how they're distributed. You sometimes see this pattern, sometimes you don't, but yeah. Something to note is points where it is overfit. So whenever you see, and this is similar to what we talked about with our linear regression as well, whenever you see like a big deviation between train and test, for example, over here, perhaps like down here as well, whenever you're seeing bigger distances between your train and your test metrics, that is a sign of overfitting. So do take note of that as well. And it is also kind of relative. So take that into account as well. Okay, so based on this, it does seem like the best K, because you have perfect, is the only one where we have perfect prediction, is at K equal to 1. Now, whether you choose to go with this or a different one is really up to you. Maybe you're trying other models. Maybe you should try a different distance metric, so on and so forth. Lots of things that you can tune here. But yeah, if you're comfortable with having a perfect prediction, I would say if you have some outside data that's completely unseen, test and see if it works too. But this data is on just like 150 irises. So yeah, yes, Dimitri.
Can you do a 0.5 or like small value?
Good question. So for K, I think it has to be an integer. I think it will say over here, it has to be an integer because it is the number of neighbors that you want to use. Something that you can add, because if you look over here, by default, they're going to consider everything uniformly. If you want to weight the closer data points higher than the further data points, you can also adjust this. So actually, you know what? Let's try that. If I'm adjusting that, we can do weights equal, what is it called again? Distance. Weights equal to distance. And just out of curiosity, let's see how it works. Oops. Is it not weights? Weights. Okay, here we go. And with weighted by distance, you can see our metrics do change, our values do change. We can be a little bit more confident about our 1 because 1 keeps holding on until like this point over here. And I believe we only have 50 data points in our test set. So pretty much every data point that is incorrect, you get it knocked down by like 2 percentage points. If that's right. But yeah. So
Thank you.
You're welcome. So yeah. Oh, before I talk about other things. So how does the number K affect the bias variance trade-off? Earlier with our graph that we saw that, there are some certain points where you started overfitting. Typically the bias variance trade-off, and this is generally for K-nearest neighbors models, might not apply to a specific data set, but generally, when you have a smaller K, you tend to overfit. So let me just zoom in over here. This red and blue, what do you call that? The boundary between the red and the blue is known as the decision boundary or decision function, which is something that was mentioned earlier. And this is basically anything that falls in the red region is going to be classified red, anything that falls in the blue region classified blue. And as you can see, K equals to 1, you have a very, very long boundary or something that's, really wrapping around every single data point. And as you increase the number K, it starts to smooth out. So this is also something that you can plot in scikit-learn. I think you can just Google scikit-learn KNN decision boundary. You can actually plot these graphs as well if you want to see it visually. But when we get to K equals to 7, you can see that this boundary looks a lot smoother already. So typically, if we're looking at K-nearest neighbors and the bias variance trade-off and the number K, this is what we usually see. For a small number K, we have low bias, high variance, which is tend to overfit. And for a large number of K, we have high bias, low variance, the tendency to underfit. Cool. And a bunch of resources down here. If you want to see K-nearest neighbors for a regression, you can also see precision recall. You can take a look at some, this is from that book that I linked on the homeroom, which is a really, really good book, but also, yeah, documentation. Cool. Any questions about this? Because I do want to talk about that function that I want you all to write. Cool. So in your project, you're going to be testing a bunch of different models. So if we're just looking at KNN, you might have like 3 different KNN models that you are trying to test. So let's just say we have KNN 1, 2, and 3. And I'm just going to instantiate 3 different ones. So let me just zoom out a little bit. Where was I? Okay, cool, here. Oops. Okay. So let's just say my first one, I want to have 5, 5 here, and I want to do like uniform for this one. And let's just say I want to do 10. And for a data set, I want to test all 3 of these models. Now, every time I use a model, there are a bunch of steps that I'm going to have to repeat, right? So what are the steps? They're mostly from over here. I would say mainly these ones. Okay. So they're mainly going to be these steps, the dot predict and also my metrics. So I'm going to want to see my confusion matrix, which is over here. Oh, I shouldn't need to import this. I know this looks really janky right now. You all are going to do a much better job than I am. You're going to have this and you're going to have the classification report. You're pretty much going to repeat these 3 cells of work for every single new model that you want to test, right? Because you do want to see what's the difference between using uniform and distance weights. What's the difference between using 5 neighbors versus 10 neighbors? If you had all of these in a single function, then you're all set. You really just have to run 1 line of code. You see all of your outputs and yeah, you're good to go. So your task, which I do want to see before you start working on your projects or as you're starting to work on your projects, is to create a function that can take in any model. And remember that these are models that are instantiated. So if this is KNN1, I guess KNN2, KNN3, what has to change is these over here. So it'll be KNN1, KNN1, here, 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 and here, and here. So this is what's going to have to change. So you see I have like my perfect predictions over here. If I want to test the second one, I'm going to have to change everything to KNN too. So with this, try and build a function that can take in any instantiated model variable, something like this, and whatever other arguments you want to use is really up to you. You can make your X-train test as arguments. You can use whatever you want as arguments really, but one of the arguments should be this instantiated model variable. So use that as a starting point and write a function that does all of these and outputs confusion matrices as well as your classification report. Send it to me via Slack. I would say before the end of next week, because all of the models that we're going to hit on, you can pretty much plug into this function and it should work fine. Any questions? Okay, one more note in your function, and I'll document what I'm saying as well and put it on Slack and on the homeroom. In your function, you should return the model variable. And I'll talk about what that is another time, maybe on Friday. But yeah, that will be your task for the week. One way to test it is to see if you like instantiate a bunch of different models, maybe you're using KNearest Neighbors. If you're still in logistic regression, same thing as well. See if you can just plug in different model variables and see if you get, different outputs, different results.
Okay, so the variable is basically just the KNN1 that you're using. So that would be the variable that you're defining in the function. And then everything else in there, scalar.fit, everything is pretty much just the same. So then it just takes the variable of whatever your model happens to be. Like if you're using logistic regression, it would take that function, it would take that variable, that class, that you define that as the variable for logistic regression, and then you would pass that in and it would work the same.
Yep, that's right.
Okay, so that's the same no matter, that from scalar down minus the variable. Essentially what you're gonna do, these matrices are pretty much what's gonna be done for every model.
Yeah, pretty much.
Okay.
Yeah, for tomorrow's models, for I think all except for one that comes from a different library, which you don't even have to use next week. We'll talk about that next week. But yeah. Oh, as Naomi was saying earlier, she asked like whether the scalar should be in the function or not, because not every model needs scaling. On Friday, I plan on talking about how you can incorporate a scalar with your model. So you technically wouldn't have to have this step in your function. However, you can also put like an argument of scale equals to true false and then scale your data if it is true. That's also an idea. Kind of up to you to design this function. It is also, once you submit it to me, it is not static. You can definitely change up this function based on what your project needs. But yeah, this function is really going to help streamline the project. I've seen students like after writing this function complete the project in like 2 days, which is definitely not what I'm expecting from you all, but it does streamline the project process a lot. And after we get into the weeds of like of talking about your function, or if I look into your function and I see that you should add something or not, we can get to a really nice function that you're going to be able to plug and play into your project. And not only for this project, but you're likely going to use it for a phase 4, likely also going to use it for your capstone. So good to get a lot of the legwork in now.
Yeah, but also, so essentially when you're looking at this part, for like what part of the function, line 7 wouldn't need to be used because you're defining it already.
Correct. Yep.
The line 7 wouldn't be needed.
Oh,
Just the
you're right.
fit one would be, because you're already defining it up above in.
Yep.
Okay.
Yeah, you're right. Cool. I'm going to document everything I said on the homeroom just so you have somewhere to refer to all the stuff that I just said. But at this point, any questions about anything that I've mentioned today? Cool. KNearest Neighbors is a pretty cool algorithm. The distance calculation and like considering of nearest neighbors is actually something that isn't only used for classification. Again, it's also used in regression, and it's also used in a bunch of unsupervised learning techniques that we'll talk about in phase 4. So the concept of nearest neighbors will come back, and it's actually one that is it is something that is easy to understand, hopefully easier to understand than our upcoming models. So yeah, it's a good one to know.
Sorry, real
mhm.
quick,
Yeah,
just to cement this. So the function is gonna have at least 2 arguments, one being the model you want to use, and then the second one being the data.
yes. In terms of data, I would say the data, it really depends on how you want to set it up. So if you want to globally define your X train, X test, Y train, Y test, and then just incorporate your function.
Gotcha. Yeah.
After,
Sorry.
it's really up to
I
you.
realized how silly the second part of the question was after
No.
you said it. Okay, I get it.
Not at all. Not at all. Like when I'll tell you when like I
Yes, so it would
defined,
be the model and
yeah.
then however many of your data variables you want to put in.
That's correct. Yeah. I'll tell you that like my first time doing a function like this, I only had the model as a variable. Oh, sorry, as an argument. And then after that, as I started like incorporating more things, also things that are outside of our scope, I figured that for my purposes, it actually made sense for me to use different versions of X train and X test. And so therefore I made X train, X test, Y train, Y test into arguments as well.
Gotcha.
So yeah, another thing that I didn't talk about before, but typically, and this might come in handy when you're trying to think about this function. Some people, and actually I did this in my own function that I showed you all for the last project as well, where I was doing a train test split within the function. It is common practice to actually use a consistent train test split throughout your entire project and then just do cross validation on your train set. I'll get into more details about that on Friday, but if you're already starting to write your function, I think that might be useful information. Cool. Whenever you have this function done, send it to me on Slack. I don't expect it till like end of next week, before the end of next week. So you don't have to do it like today. But yeah, I'm gonna put the instructions on Slack as well as on the homeroom later. Nice. Any final questions before we close out for the day? Cool. So tomorrow's model is actually going to be one that is probabilistic. I guess, yeah, it's a probabilistic model. It's actually going to call on Bayes' theorem again. So get ready for some Bayes' theorem again. Just a sneak preview. But yeah, if there are no other questions, don't forget to submit your blogs. Please submit your blogs. The sooner you get it out of the way, the better, really, in my opinion. It doesn't have to be like super in-depth or anything, just 500 words. And yeah, awesome. Well, if there's no further questions, I will talk to you all tomorrow at this time. And anything else, just let me know in Slack. Cool. Have a great rest of your day, everybody. Bye.